Every modern programming language relies on a hidden engine to translate human-readable source code into machine instructions. Tools like Yacc handle this heavy lifting. Inside the compiler pipeline, this phase is called syntax analysis. It takes raw text tokens and structures them according to a language's specific context-free grammar. A bottom-up parser scans the input buffer from left to right, building a derivation on the state stack. But it only has access to its current state and a single incoming token, called the lookahead. Based on that limited view, it has two choices. It can shift, pushing the new input token directly onto the stack, or it can reduce, collapsing a completed grammatical handle on the stack into a single structural node. The system breaks down when it hits an interception where the grammar legally permits a shift and a reduce at the exact same time. This shift-reduce conflict prevents deterministic code compilation. The parser freezes, unable to identify which path guarantees the correct syntax tree. Designing a compiler requires engineering a mathematical state machine capable of resolving these local ambiguities automatically without second-guessing itself. Consider a standard variable assignment, mathematically represented as an L value equaling an R value. This grammatical construct reliably breaks basic parsers. A simple LR parser, or SLR, attempts to make the shift-reduce decision by consulting a global list. If it considers reducing a phrase, it checks its follow set, a list of all symbols that are ever allowed to appear after that target anywhere in the language. This graph illustrates the LR0 automaton. If we look closely at state 2, the parser holds an L value on the stack and is looking at an incoming equal sign. The shift logic evaluates ethically. The parser reads the equal sign, matches it to the first rule, and prepares to shift it. At the same time, it evaluates the reduce action. The parser checks its global follow set for the non-terminal R. Because an equal sign is allowed to follow an R in other parts of the grammar, the equal sign is on that list. The SLR logic dictates a reduce. Now the parser attempts to execute both a shift and a reduce action simultaneously, triggering a fatal conflict. The parser is operating on flawed context. The equal sign is globally permitted to follow an R, but in this specific derivation path, applying that rule creates an invalid syntax tree. Relying on global rules generates false positives consistently when parsing complex, nested languages like C or C++. Global context lacks specificity. To compile real-world programming constructs, the parser must track exactly what is allowed in the current localized state. The canonical LR1 parser solves this by discarding global assumptions in favor of absolute, localized precision. It changes the anatomy of the parser state itself. It takes the base grammatical rule and bolts the exact valid lookahead symbol directly to it. The operational mandate becomes incredibly strict. The parser is explicitly forbidden from making a reduce action unless the incoming token matches this attached local lookahead perfectly. This surgical precision filters out the false positives. By ignoring the global list, the shift-reduce conflict is bypassed entirely. However, achieving this exactness carries a severe architectural penalty. If a core grammatical rule has multiple valid lookaheads, depending on how the code is nested, the parser cannot generalize. It must generate completely separate, parallel states in memory for every single variation. We see this directly in the table generation. A single base node splits into multiple duplicate nodes, sharing identical core logic, but carrying distinct lookahead tags. This duplication cascades, recursively multiplying the state graph across the entire grammar structure. The math scales poorly. A language parser that requires 300 states under the SLR model balloons to several thousand states under canonical LR1. The accuracy is flawless, but the resulting memory footprint makes the model prohibitive for practical compiler engineering. The lookahead LR, or LALR architecture, was designed specifically to cure this state bloat. To do this, we define the core of a parser item. The core is the base production rule and the current position of the parsing dot, entirely ignoring the attached lookahead symbol. The LALR hypothesis dictates that any separate states in the graph possessing identical cores can be safely collapsed back together without destroying their lookahead data. This graph maps the sprawling LR1 network. Scanning the structure, we find nodes like I3 and I6. Their core components are identical, only the lookahead symbols differ. The algorithm takes these redundant states and physically merges them. I3 and I6 are fused together to form a new state, I36. the specific look-ahead symbols are preserved, pooled together into a single mathematical set inside the newly merged state. This powerful merging operation now sweeps across the entire parser network, aggressively pruning away the duplicated redundant pathways. The LALR graph shrinks down to the exact minimal footprint of the SLR parser, but successfully retains the granular look-ahead precision of LR1. While LALR merging will never introduce a new shift-reduce conflict, it can technically create rare reduce-reduce conflicts. Language designers easily route around these edge cases. LALR extracts the absolute accuracy of the LR1 model and maps it onto a memory-optimized footprint. Moving from theoretical state graphs to functional software requires looking at how tools like Yacc physically generate C code. A parser generator outputs its logic as an actionable two-dimensional matrix, split into an action table for shift and reduce commands and a go-to table for state transitions. This matrix visualizes the resulting data structure. For a standard programming language, this grid requires tens of thousands of individual cells. A close inspection reveals heavy redundancy. Vast sections of the array are empty error cells, and many populated rows are completely identical. To fit this logic into constrained hardware limits, the compiler applies parsing table compaction. Instead of storing a massive two-dimensional grid, the algorithm identifies identical rows of actions and collapses them. It restructures the data so multiple parser states point to the exact same location in memory, using a base pointer and terminal offsets to extract the correct action on the fly. This technique compresses the 2D matrix down into highly efficient one-dimensional lists. By optimizing the data structures directly at the byte level, complex compilers execute rapidly on almost any device, regardless of memory limitations. LALR parsing balances the need for rigorous theoretical exactness with aggressive real-world efficiency.